Welcome everyone. My name is Daniel Timme. Today I'm going to be talking about some work or sharing some work that I've done with my PhD committee down at Florida State University over the last year and a half, and I'm going to do my best to do that in 8 minutes or less. All right, so this is particularly important to us because systems are becoming more and more complex. Not only are they becoming more and more complex, but process monitoring in general is becoming more and more complex. And we're also becoming more and more interested in automated data collection. And oops, my slides are cut off. That's interesting. I'll do my best. Automated data collection and analysis, I believe the buzzword these days is machine learning. And when your practitioner generally won't know the underlying distribution of what they're working with. So we're going to be using non-parametric modeling because it allows us kind of a workaround for that. When I say we're interested in higher dimensional modeling, currently there's a lot of work that's out there for univariate, but not a whole lot that's currently for the multivariate case at this point. We're going to be using regression trees and random forests to do this, and that's nice because they're easy to build, interpret, understand. And we're basically going to be adding a tree or a, oh, there they go, look at that, that's sweet. We're going to be adding one at each time step. The Kolmogorov-Smirnov statistic, what we're using for our monitoring statistics, we like this because we're basically taking on the error head on. So if you think of in control, you're operating in the presence of natural variation or background noise. When you're out of control, you're now beyond, you have noise beyond that of the background noise. So if you put that in the Kolmogorov-Smirnov test, you're able to compare the distributions, our case empirical distributions on the residuals, and we should be able to identify whether we are out of control or in control. So we're going to do this using change point detection, which is often used in conjunction with statistical process control. And ideally, we like to be able to identify if a process is out of control in T profiles given M historic profiles. Now, a profile is defined as the functional relationship mapping from one dimension into the other. And we're going to be denoting our in control profiles as F and our out of control profiles as phi. And we're going to do all this via simulation study. So our independent variable is going to be sampled from the uniform distribution with for values between 0 and 1. It'll be 3 dimensions. And we were sampling our noise from the normal distribution with a mean of 0 and a variance of 1. So our functional relationship for F and phi will be from 3 dimensions to 1 dimension. So we're going to be working with 2 in control profiles, 1 linear, 1 nonlinear, 3 out of control forcing functions, a sinusoidal, 1 non-differentiable, and 1 localized change. We're going to be dealing with both 20 and 40 historic profiles. And then we're going to define the time step of the very last in control profile to be that of tau, which we'll be using 0, which would be the case if we are out of control right away, only using the historic profiles. And then 30, which means we'll have at least 30 in control profiles before introducing the out of control profile. And we'll be doing this for signal to noise ratios of 3, 5, and 7. I'm a sucker for flowcharts. So as I mentioned, we're going to sample our independent variables from the uniform distribution, noise from the normal distribution. And recall I said that tau is the last in control time step. So when time is less than tau, we're going to use our in control profile, which is f of x. When time is greater than tau, we're going to use our out of control profile, which we denote as phi of x. We're going to fit a regression tree or a random forest to this profile. And then we're going to find an estimate using the current response, but all of the previous trees or forests. So we're going to have a whole bunch of estimates. We're going to take the mean of those estimates, and that's going to give us a prediction. Now that we have a prediction and we have our response, we can easily find the residuals. Then we're going to take do the Kolmogorov-Smirnov test using the current set of residuals against all previous sets of residuals, which will give us an array of monitoring statistics, to which we simply take the maximum of that and compare it to our upper control limit, which we find 2 different methods, a single bootstrap and a double bootstrap. Don't have enough time to go over that now, but I will be more than happy to describe that during my poster session when you all come by, because I know you will. We're going to compare this to 2 methods that are currently out there in literature, and using 2 different performance metrics, one being a false alarm rate and one being an average run length. So the methods we're going to compare to are that of Lee et al., who used a support vector regression for their profiles, and we'll use exponentially weighted moving average to determine for their monitoring statistics. Actually, 5 of them come from the Williams et al., but they only use 3 of them in their, they only recommend 3 of them. So we'll be comparing to those 3, and that of Gucci et al., which is a single index model for his profiles, or their profiles rather. And then they use the coefficients of their model, and take the L2 norm of that for their monitoring statistics, pardon me. So a false alarm is basically when you identify something's being out of control when you're technically in control. And we get the false alarm rate by saying that the total number of false alarms you have divided by the total number of trials plus those false alarms. So overall, the total number of restarts. And what we found is that each of our methods actually outperform the methods in literature when it comes to false alarm rate. Now, you might notice that for the nonlinear case, it is much, much lower. And there's a reason for that. It has to do with the upper control limit, but you'll only find out if you come to my poster. Second one is average run length, and that is exactly as it sounds. It is an average run length. So a run length is if you take the time when you properly identify as out of control, as big T, and you subtract out that last in control time step, which is tau, and you take the average of that over all your trials, you will find the average run length. Yay, statistics 101, right? We did two different things. As I mentioned, we had 3 out of control forcing functions. For the sinusoidal and the non-differentiable, we actually found that we were able to flag perfectly to be an average run length of 1 every single time. When we compare this to the methods of Lee et al., we were able to outperform them in every single scenario. As for Gucci et al., they also were able to identify with an average run length of 1 in some scenarios, not in others. So we were either able to outperform them or tie them. For the localized change, we actually did this because we were able to identify so perfectly. We want to make sure we could break our model, which we did. We only compared that to the Gucci et al. Because we were able to outperform the Lee et al. Method in every single scenario. So we only show the results there. And what we found is sometimes we can outperform them, sometimes they could outperform us. All right, so I'm gonna go ahead and wrap all this up. We were able to, as I mentioned, false alarm rate outperform all the other methods. When it came to false alarm rate for the average run length, the Lee et al., we were able to outperform them for the sinusoidal and the non-differentiable out of control forcing functions in every single scenario. For the Yaguchi et al. Method, we either outperformed them or we were able to tie them. So we only compared that method for the localized change. And overall, they were able, single index models actually able to outperform us more often than we were able to outperform them. But we did find that the results were actually very, very close in almost every single scenario. More secrets I can share with you at the poster session when you come by. So the biggest strength about our method is very, very, very versatile. So in that flow chart that I kind of had to speed through in the speed talk, I could put in any kind of model I wanted. That's why we used random forest. We originally only started with regression trees, but we were able to plug random forest in there. I can plug any model in there as long as I can obtain residuals and do this. Same thing with the measure. We use the Kolmogorov-Smirnov test for our monitoring statistic. I could use anything in there that I would like to do. One thing about the Kolmogorov-Smirnov is it gave us a discrete monitoring statistic. So we had to get a little creative whenever it came to comparing to the other methods that have continuous monitoring statistics. But we are currently actually working on something to kind of work around that and still have a strong measure. It's clear as mud. All right, any questions? Thank you.